Yeah, it's important, I suppose. I mean, it is. Why does motion keep coming up in calculus? Maybe we should go back to, hey, you guys have your notes. You don't need me to open up files to show you. My question to you is, as I open up your book, just because sorry, there's a weird new page because it updated. As I get your textbook open, just in case we need to look at any of the information, because as we talked about real quick at the beginning of class when you guys were powwowing, most of you, from what we did yesterday, should have been able to read a problem and at least kind of know what they were asking you to find. Acceleration, velocity, position, time. You should have known at least somewhat what they were asking you to find. The problem came probably in determining the givens and using the givens. Determining the givens and using the givens. Finding out what they gave you and figuring out where to put it, basically. And maybe just a few of you got stuck a little bit on the math of how to solve once all of that had been figured out or analyzed. But motion. Where are we at? Chapter 4, section 2? No, section 1 at the end. Do you guys know what page homework is on? 287, thanks. It just saves me a little bit of time. Gracias, because that was all the integration stuff, huh? Okay, so as I get the book open and ready for us to be able to process not only what you were supposed to find, but what you were given and how to put it all together, I want you guys to look in your notes for where we first talked about calculus. Look in the table of contents. Where did we first talk about calculus? Preview of calculus. Yep, that's what I was thinking. Preview of calculus. What's on it? Maybe you didn't. I think everyone was supposed to write down at least a little bit. Calculus. How did I describe calculus in the preview to calculus? The mathematics of change. Why are we talking about motion? What's the most practical application of things changing? Motion. Yeah. Now, technically, specifically, we're talking about position, velocity, acceleration. We're talking about objects in motion, objects in movement, right? This is totally random and off topic somewhat, but thinking about motion, has anybody ever seen the exhibit Bodies in Motion? No? No? All last year, driving down, was it Reseda? There were these huge banners for the Bodies in Motion exhibit. They're the ones that are like super crazy and they're actual like, would you say petrified? I'm not very scientific. But like the bodies and like you can see their muscles in movement and they've been positioned certain ways to show like what's acting in different ways with the tendons and with the, anyway, it's crazy. I haven't actually been brave enough to go, but I've seen pictures and I've had friends that have gone. Anyway, in motion, like our world is in motion, sometimes too much motion, right? We deal with movement every day, but not just physical movement. Right? Don't our bank accounts or your parents' bank accounts have motion? Doesn't the stock market have motion? Right? When you're filling up a cup of water, isn't that motion? Now, is that like the normal like cars moving and objects or people walking and things falling? Well, no, I guess not. But isn't it still change? And there are rates of change. What's the instantaneous rate of change called? That's initial velocity. Just basic. Get away from the velocity acceleration position. Just instantaneous rate of change. What am I talking about? A derivative. How much have we studied derivatives? A lot. So if motion deals with rates of change are derivatives. Half of calculus 1 is derivatives. What are integrals? Finding anti-derivatives. Oh my goodness, derivatives are important all year. Forwards or backwards. So why is motion important in calculus? Because calculus is the math of motion. So is this important? Yes. But is it brand new? No. Every time you find a derivative, every time you find an antiderivative, there is an application to something to do with motion. Literal watching motion or rising, falling, quantities, amounts, etc. motion. Okay. With that, just to kind of put it in context, because some of you are like, motion, whatever, it's one of those applications I can just ignore. It's kind of all of calculus, minus the technicalities of how to derive and how to anti-derive and how to look at a graph and how to look at a table and how to use your theorems. Like, there's all these intricacies to dealing with motion, but everything is about motion in calculus, because that's what calculus is the math of. Okay, so come in here. Bloop, 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 bloop. Starting at number 54, letting you guys check the final answer. You started from gravity. Did you start from the right gravity, meters per second squared, hopefully? You could have gotten your velocity equation. You could have gotten your position equation. Quick heads up, they're labeling position at least sometimes with f of t. And the next problem, they do x of t. I don't know why. Whatevs. You could have called it whatever you wanted to. But when they finished plugging in, they got the position equation to be. Okay? The position equation to be. How did they find the max? Could they have found the vertex of the parabola? Sure. H equals negative b over 2a. That's a pre-cal formula. That's the x, and then which is the t, and then plug in to find the y. Or just say at the maximum height, what's velocity going to equal? Did we talk about that yesterday? Hopefully you used it. Long story short, your time ends up being 10 over 9.8, but they weren't asking, did you look at the find? They weren't asking for the time. You just had to find that to plug in to find what they were actually asking for, which was the, not the when of the maximum height, but the where of the maximum height. They wanted the, I know it looks weird, the position, x of. Did you guys plug in and get 7.1? Pause. How many decimal places do we need for the AP? 3. What was the answer with 3 decimal places? 102? Thanks, Ryan. 7.102. Moving on. Hey, what was the example? What was going on in number 54? Did they tell us anything about like what was moving? Baseball thrown up, coming back down, which makes sense with the negative parabola, right? Wait, hold on. Just a few of you might remember that I said that we weren't doing two-dimensional motion, meaning there is no moving horizontally and vertically. Some of you might get confused with the downwards parabola. You're like, wait, I thought we weren't doing that. We're not. We're throwing the baseball straight up and it's coming straight down. Why is there a parabola that goes out? Position is your y. What's your x? X of t. Is time still moving when you throw a ball up and you throw a ball down? So as time moves, it's going higher and then coming lower. I'm not literally throwing it out. We would need x of t and y of t to do that. I'm throwing it straight up and it's coming straight down, and if I don't move, it's going to bonk me on the head. But time spreads out the function. Okay, anyway, coming back. Number 60. Choop, choop. What's the scenario? We have to set the scene. Is it a ball? Is it a car? Is it nothing? Okay, so like a particle on like a line sort of thing? Okay, the AP loves to do particles on lines. I don't know. Keep calling him Bob if that helps. Bob goes all over the place. So we have a position function is our given. This is like old school. Were we just supposed to go from position to velocity by taking a derivative? Huh. How did you guys do it? Did you do product rule, chain rule, or did you multiply it all out and then take a derivative? Okay, you can multiply it all out. But if you did, remember, you have to square this guy first using foiling, t squared minus 6t plus 9, and then using polynomial multiplication. Did anybody try product rule, chain rule? Only one? I don't know. To be honest, some of you guys, I think I'm more worried about your multiplying out than I am about your product rule. But how many of you guys got letter A right? Okay. But for the majority of the class, doing the exact same way, that's not a very high percentage. So let's talk really quickly about how you would do the product rule, chain rule. So Patricia, just keep me honest, okay? X prime of t is equal to, don't we have a first and a second, guys? Remind me of product rule, because doing integration, the derivative rules kind of deteriorate until we practice them again. So what's the product rule? Second. D first, isn't that just one? Plus? How do I take the derivative of u squared? U prime, I need that, but first I need 2u, good, times, what's u prime? Oh, ugh, but you still have to multiply. No, you don't. Why am I taking the time to go change my silly marker to be, oh, no, I don't want that. Yes, I'm still taking time. Hold on, this is going to be easier if I do this and then I do this. Yes, I'm still taking time. I don't like wasting time, do I? So why am I doing it? To green. Find what's common. The green trick, we've been talking about it all year. Did you think about it? I'm trying to save you from yourselves, at least to some extent. It's going to be easier on your brain if you see there's a common. And it's going to save you on the problems that I know are coming on the AP. Taking out a t minus 3, what's left? Just a 1 times t minus 3 plus 2 times t minus 1. Oh, this is confusing. No, it's not. Look at that. It was way easier than multiplying that out. Isn't that just t minus 3 plus 2t minus 2? Should you be able to do that? Yes. Your kids don't. I don't know why. But what do we get? 1t plus 2t is? Got it. So you figure out what went wrong and figure out what you needed to do right. This was a simple taking a derivative to find velocity, taking a second derivative to find acceleration. Should you stick with your multiplying out? Did you get this? And if you didn't, or if it took you a while, why not just go take a derivative and do the green trick? Just a heads up, just a heads up. Okay, we have our velocity, we have our acceleration. This can be factored. Oh, look, mine ended factored. I didn't even have to factor it. You're welcome. Letter B. Ooh, do they say something about when it's moving to the right or moving up? Moving to the right. Why did I know that? What do I see? Velocity being positive. Oh, they're caring about the sign of velocity, aka they're caring about the direction of the movement. How on earth, they made a huge jump that some of you don't like. How on earth did they get intervals? They showed no work. What have we done this year where we've been finding signs of derivatives? First derivative test, the sign chart, right? Increasing, decreasing of position came from positive negatives of, sorry, I should say increasing, decreasing of f came from signs of f prime. How do we analyze signs of a prime? Sign chart. How do we do a sign chart? Find the critical numbers. What are the critical numbers? T equals 3. Good. So couldn't we, for letter B, couldn't we have done a quick little sign chart and been like, I start at 0 because they told me to start at 0. I'm going to 5. Cool. And I'm plugging in 5/3, which is approximately, well, it is 1 2/3, and then 3. What should you have done? Tested the signs of velocity. And then you could figure out, basically, the left, right of position. It's just an application of a sign chart. And because I can see the answers without taking the time to actually plug and chug into my velocity function, it should have ended up being positive, negative, positive. So guess what? When is it moving right? Here and here. Oh, what's it doing here? The particle is moving to the left because velocity is negative. Do we know that greater than 0 means positive and less than 0 means negative? Hopefully. Letter C, what was the wording? Because the math is easy. Set acceleration equal to 0. Find the velocity when? Oh, when the acceleration is 0. So they told you set equal to 0, basically. Cool. So taking an acceleration, setting equal to 0, that was not your answer, but it is a means to the end. Your 7/3, plug it into the velocity function, and done. Negative 4/3. Or you could have been super smart alecky, but smart. And stuck it to the man. Are we cool? How many of you guys missed at least one thing on number 60? Okay, do you see why I went over it? Cool. But we're all right? Okay. What else do we have? Oh, and 64. Okay, let me let you guys just peek at 62. Although hopefully you realized acceleration was not constant. Oh! But that's okay. If it's not constant, still just integrate the same way we do with the constant acceleration. So sine of t plus c. Where did some of you guys make a mistake? Actually, I don't think you would have caught it there. They gave you an initial velocity. Did they say something? Is it something being dropped, or did they actually tell you initial velocity is 0? Oh, initially at rest. Okay, good. That's another way of saying it. Initially at rest, another way of saying velocity, initial velocity is 0. But the problem is, some of you would have been like, oh, c is 0, and then moved down to here, and then been like, oh, c is 3. But it's not 3. Did anybody think that the position c was 3 instead of... What did you do? I know this because Lorenzo actually did this homework 2 nights ago and came in with this question yesterday. So no, I don't have them all memorized this well. But this one, you had velocity is equal to sine of t plus c. Why was c 0? The velocity was 0? Not necessarily. Technically, as soon as we have a non-constant acceleration, we actually need to plug in chug to see what c is. C is only the exact same thing as initial position, initial velocity, if I have a constant acceleration. That's why I kept saying that over and over and over again. Otherwise, it's a clue. It's a clue we have to plug in and say, hey, what? But guys, what is sine of 0? 0. And what was my initial velocity? 0. So what did the first c being 0? But it was kind of just an accident. Just happened to be the same thing as the initial velocity. But check out position. Your initial position, which is the same thing as x of 0, is equal to 3. And so a lot of you guys were like, yay, plus 3. X of 0, which is 3, has to be negative cosine of 0 plus c. I don't have a constant acceleration. When we plug in 0 here, it's not. When we plug in 0 here, it's a 1. So mathematically, the reason why we plugged in shortcuts, initial position, initial velocity for c's with constant acceleration is everything always canceled out. With those, they were polynomials, and all the t's being 0 canceled everything but c. But here, with trig, that's not necessarily true. Sometimes, yeah, but sometimes no. Do our antiderivative work when we were given a point and say, I don't know, plug it in, find c. What did c end up being? Now do you see 4? So we had our, here we go. We have our velocity there. We have our position there. I think that was letter A, getting to position. And then letter B, is it talking about like maximums or something? Or when it's at rest, when it's stopped? When it's at rest. How do I know that it had to be either a maximum or at rest? Because both of those clues lead you to velocity being 0. So when is sine 0? I don't know. Every pi. Exactly. And that's what they said. You could have done pi n. They used pi k. That's awkward. Whatever. I would have used pi n, with n being 0, 1, 2, 3, 4, 5, 6. Infinitely many answers. I had to put a little baby clue. Last one, number 64. No. You had to convert? Did you guys convert? Possibly not. Why did you have to convert? Did anybody realize they gave you a clue in feet, but the rates were in miles? Ugh. Why'd they give you rates in miles per hour? It's a car. What's your speedometer say? Miles per hour. What does the speed limit sign say? Okay, it makes sense they gave you miles per hour, but if you're only traveling for like 1 or 2 seconds, does it make sense you're going to measure that in miles? No, you're going to measure it in feet. How do you convert from miles per hour to feet per second? Don't you multiply by a bridge of 5,280 over 3,600? Have to change miles to feet and then hours to seconds. So if I were you guys, I would make yourselves a note that you need to be aware of the units. And if somewhere down the line it says feet, I don't think I should be dealing or staying in miles per hour. So we multiplied 45 miles per hour times 1 mile over, 5,280 feet over 1 mile to get to feet. And then times 1 hour over 3,600 seconds to get to seconds. Dimensional analysis at its best. Zoom, zoom, zoom. Now you should basically take all of your equations and wherever you plugged in 45s and 30s and maybe even 15s, plug in 66s and 44s instead. That's going to make a huge change. So what I'm actually going to do right now is pause and wait on this problem because some of you need to say, oh, wait, I was using the wrong numbers. I have no idea. But if I were you, I would go ahead. We'll talk about this one tomorrow real quick, see if we have questions. Get down the final answer. I don't see an A, B, C. Were they basically just... Oh, that's confusing. Was this the final answer? Was it a where or how far? Oh, got it. This was the initial velocity, and that's a velocity at some time A and some velocity at some time B. Got it, got it, got it. So yeah, the how far, the final answer is 117.33 or 0.33. I don't know. So final answer, 117.33. This, put a star by it, play with it. But for right now, weren't you guys talking about 117.33? It's the final answer, and these are the converted speeds. Weren't you guys talking about odds? Okay, so let's pause. Instead of going over an even entirely and not letting you think about it again, let's go over the odds that you knew you were stuck on and you knew the answers to. So is there something that any group or any individual person wants us to peek at? 63. All right, all groups, I want you to shift your focus to 63. Either you're going to be able to give us insight and help as to where to go, what to do, or you're going to be looking for the answers. You're going to be looking for some help or you're going to be giving help. So look at number 63. Real quickly, I'm looking at the directions way up here. Position is, okay, our little particle P, Bob is moving along the x-axis. We have x, we have velocity, we have acceleration. All right. Number 63. Let me grab him. Car is traveling at 45 miles per hour and brought to a stop. I'm doing the one that you guys just talked about. Thank you. Maker of an automobile. My brain was still on 64. That's the one you guys are supposed to be doing. Called it. The maker of an automobile advertises that it takes 13 seconds to decelerate with 64, from 25 kilometers per hour to 80 kilometers per hour. Assume the acceleration is constant. So from yesterday, remember how I would always analyze? 13 seconds to accelerate from 25 to. Okay, so couldn't I say that my initial velocity is 25 kilometers? For this scenario, we're starting at 25 kilometers per hour, right? And then some velocity at some other, you could call it A. If you want, you could even call it B. I don't care. Some velocity at some other time is going to be 80 kilometers per hour. Maybe we should do some dimensional analysis. We'll figure that out in a second. 13 seconds. Oh, wait a minute. 13 seconds. I know it's not just V of B. Isn't that V of 13? Does that make sense? So when time is 0, we're there. When time is 13, we're there. Assume the acceleration is somehow we're given a constant acceleration, but did they tell me what it is? No. Can I use gravity? Not unless the car has fallen off a cliff. Let's not have it do that. Let's have it be on a road. Is that cool? Okay. I thought so too. Letter A says find the acceleration in meters per second per second. Ooh, is this good? No. So what am I going to do? Convert. So the very first thing we should do, just like your number 64 with miles per hour and feet per second, we should convert. Is it okay if I do 1,000 meters over 1 kilometer? And is it okay if I do 1 hour over 3,600 seconds? So then shouldn't I do the exact same conversion down here? Did anybody do that conversion and have it for 25 kilometers per hour? Like that? 250. Thank you. That does reduce, though, right? Can we divide both by 2, by 4, by 6? I think just by 2. So 125 over, no, sorry, 18. Is that right? Okay. And then who has this one? 800? Oh, times 1,000. Haha, silly me. Thank you, Rachel. Because the 2 cancel and then you have a 0. That makes sense. And then we could reduce that by the same thing? Just like, no. Is 4 go in? Yes. So I could do over 9, and I could do 2,000, right? Okay. Oh, sorry, I put the wrong 0. Thanks, guys. Good? Now good? Okay. Find the acceleration in meters per second. Well, how on earth are we supposed to do? These are velocities. What's your velocity equation if my acceleration is constant? How do we get there? A sub 0, t plus, right? And we can only put the plus c to be v sub 0 because if I plugged in 0, my initial would be c. So don't I have stuff to plug in? Can't I say v of 13 is equal to 200 over 9 is equal to a sub naught times 13 plus v sub naught, which is 125 over 18? Is it possible to find your acceleration? Head nods. There we go. Good. What's letter B say? Pause. Translate. Distance. Who am I looking at? Position. And then it says during the... So what do I want to find? X of 13. How do I find x of 13? Don't I have to start with x of t? How do I find x of t? Yeah. You see it? So can't I just go ahead and do 1/2 a sub naught t squared plus v sub naught t plus x sub naught? Are you going to find your a sub naught? Booyah. Plug it in. Do you already know your v sub naught? Booyah. Plug it in. What's your x sub naught? This is where it gets a little confusing, but anyone with any training in physics will tell you how to deal with this. Nick, we might come back to you. What's your initial position in this problem? That's okay. Nick, what would you say about your initial position? Anything? Exactly. 0. Why? Physics, you can take any situation and say, I don't know, but wherever it's starting, that can be 0. Unless it needs you measuring from something. If you're on top of a building talking about ground, maybe you'll make ground 0 and this 500 and, I don't know, whatever, 20 feet. Or you could just say, whatever, top of the building is 0, ground's going to be negative 520 feet. You can make it point of reference what you want it to be unless they say something specific. So do I care how far the car is from like a start line? Or how far it is from the stands? Or how far it is from home? Do I care about where the car is? No. So what's your initial position? 0. We can make it literally nothing. They didn't tell us anything. So didn't make it 0. So kiddos, all we have to do is plug in 13. And we're done. Is that cool? Yeah. 53? Specifically A, because you need to get started? Okay. They're telling us to use negative 32 because we're doing feet. That's gravity. We know that, yeah? Gravity is acceleration. Specifically A. Because if you can get A, then we'll see how you do on B. A balloon rising vertically with a velocity of, sounds like initial velocity to me, right? Releases a sandbag at the instant it is 64 feet above the ground. If you want, could you do a little like, with a little sandbag? Pew, 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 pew. Yeah, whatever. Mary Poppins. Anyway, so a velocity of, so we have our initial velocity. Releases a sandbag at the instant it is 64 feet above the ground. So at some point, x of, we could say b, because it doesn't tell us how much time. I'm putting into position 64. That's not a velocity, that's a position. Okay, so something happens at 64. How many seconds after its release will the bag strike the ground? Are we actually caring about the balloon's motion or the sandbag's motion? Sandbag's motion. Is the sandbag's motion still going to be 16 feet per second for an initial velocity? Yeah, because he's traveling with the balloon. Literally, Mary Poppins, right? He's traveling with the balloon. He must be a happy sandbag. So, sandbag's rising. He has an initial velocity of 16 feet per second. He gets released. He's going to start, gravity's going to start overtaking, right? So what are we asking? Strike the ground. What do we know? Position at some point equals 0. So if you want to, we could technically go ahead and make this A, kind of like how we have A be the first and B be the second, or like physics, initial and terminal. That could be our initial position. It starts off 64 feet above the ground, going with an initial velocity of 16 feet per second. The balloon is gone, so now gravity is going to take over. X of B equals 0. Well, how do I get a position function? Don't we know acceleration is negative 32? Can't we find velocity is equal to negative 32t plus initial velocity, which is 16? Double checking feet per second squared, feet per second. I don't need any bridges. I don't need any dimensional analysis. Can't I now go to position and get it to be 1/2 or negative 16t squared plus v sub naught t plus x sub naught? What's my initial position? Booyah. Is that equal to 0? Factor. Are we cool? Cool. All right, kiddos, with that, we don't have a lot of time, but that's okay. I didn't actually expect us to. Let's go ahead and go peek at our packet. I want you guys to grab out, just use your pencil. We're going to circle the ones I want you to try tonight. Sound good? We're going to circle the ones I want you to try tonight. Example number 1 gave us a table. We worked through that together yesterday. Some of you might need to go back to the page and kind of think about it a little bit more. We ended off with MVT and we did it pretty fast, but long story short, we read the whole must there be a, which is theorem terminology through and through, like your card. It said acceleration is 0, which meant V prime is 0. That's like Rolle's theorem. Special case. So we did MVT and said, hey, when will MVT be 0? When will the derivative be 0? Well, that happens when V of A equals V of B. Will that ever occur? And we said, oh yeah, between 6 and 12. Since V of 6 is 5, which equals V of 12, then there must be, technically, there must be a time, well, let me put it in parentheses. The time will actually be between 6 and 12. So yes, between 0 and 12, but I can say even more specifically, it's actually going to for sure happen between 6 and 12, just to be a little more specific. This one, you're not given a table. What are you given? A graph. I want you guys to circle number 1. You should be able to do it. Number 2, you should be able to do it. Number 3, you should be able to do it. Number 4, you should be able to do it. Number 5, you should be able to do it. But let's give ourselves a couple hints first. So all of example 2. Sorry, it took me a second. The AP would sometimes ask extra questions of a graph like this you couldn't do yet, but you can do all of these. Hey guys, who is this a graph of? Velocity. Good. And if they're asking about moving right or moving left, who are we looking at? Negative or positive of velocity. So wait, if this is a velocity graph, can't we say the y values are the velocities? So you might want to make a hint. Look at the y values. Look at the y values for 1 and 2. Hey, number 3. Number 3 says acceleration. Wait, who's acceleration in terms of velocity? Like, how do they relate? Velocity prime. Wait, how do I think about, if acceleration is velocity prime, how do I think about a prime looking at a graph? The slopes of v, or the increasing, decreasing of. Do you guys see what you're supposed to do? Tonight, I want you guys to play with number 64 again. I want you to do example number 2. Give me one more second. And I also want you to do example 3, but only 1, 2, and 3. Example 3, but only 1, 2, and 3. Don't put an X through 4, just circle 1, 2, and 3. We're not ready for 4. All right, cool kids, see you later. Example 2, example 3, everything but the last on example 3, and play with 64. Look at you in motion. Calculus at play.